It's my great pleasure to introduce our next speaker, Jingbo from Department of Mathematics, State University of New York at Buffalo, who will talk about operators on the Drury-Arveson spaces. Jingbo, please.
Okay, thank you. Thanks for the introduction. So first, let me just thank the organizers for organizing this this workshop. It's a great opportunity to talk about these things. So so this talk will so this talk will be a survey about some of the results the Drury-Arveson space. Now, we've heard quite a bit about the Drury-Arveson space from Michael's two talks so far. So a lot of things that I'm going to say are actually going to overlap to what we have already heard. But perhaps I'll offer some different perspective. I mean, you will see some of the same material, but perhaps from a slightly different point of view. Okay, so the story of Drury-Arveson space, goes back to fundamental inequality for contraction. I think that's a situation that everybody is familiar with. So this is an inequality that goes back to 1951. If you have a contraction, then you apply a polynomial to it. Its norm is dominated by the supernorm of the polynomial on the disk, on the unit disk. So, so once you have that, then you have, you sort of wonder, so how do you generalize this to tuples of operators? So if you consider commuting tuple, then I think the first thought might be that you try to do it on polydisks on the right hand side. So if you apply a polynomial to a tuple, you look at its norm. So the first thing you think about is this inequality, does that hold? Well, I mean, we know now that it holds if n is 2, but it fails if n is at least 3. Now, so you have to ask why. So basically there are these issues. So first of all, what's the right notion for contraction? Not right notion for contraction for commuting tuple operators. And then, what's the right domain for the right-hand side? And then the question is, what's the norm? So, so all of this was figured out by 1978. So a commuting tuple A1 through AN on a Hilbert space H is said to be a row contraction. If this combination here is a contraction, namely if its norm is less than or equal to 1. So another way of saying this, and you've seen this in Michael's talk, is that so the equivalent statement is this inequality. And that's why it's called a row contraction. So the point is that this is a stronger requirement than just a requirement that these individual operators be a contraction. So so the fundamental inequality for the row contractions is this. So this first appeared in a paper by Drury in 1978. And then, of course, it also appeared in Arveson's paper in 1998. So if you have a tuple A1 through AN that is commuting row contraction, then this inequality holds. So what that holds for every multivariable polynomial, or polynomial P. But what needs explanation is this norm on the right hand side. So what is this this norm? Well, this turns out to be what's called a multiplier norm on the Drury-Arveson space. So now, if nowadays, if you write a paper, you start introducing the Drury-Arveson space, you quite often you just go with the most convenient definition. So you would just go with this definition, just write down what the definition for inner product is on the space of analytic functions on the unit ball. And that's this. It's given by this formula. So now, so this space. So you have it's easy to see that you have this as the reproducing kernel for the functions in the space, in the sense that if you have a function h which belongs to the space, and its value at the point of z is simply the inner product h was this kernel kz. As Ken Davison mentioned yesterday, I think Arveson was the first one to actually write down such a formula. So he was the first one to recognize that the space that we call Drury-Arveson space now is actually reproducing kernel space. This actually makes a huge difference. So a lot of things you do, analysis and so on, and we've seen in the talks today, yesterday. So a lot of things you do on the space actually depend on this kernel. You have to analyze in many different ways. So knowing that you actually have such a reproducing kernel, that's really important. But the space itself actually has a longer history than that. So Michael also mentioned this in his talk yesterday. So in 1977, Art Rubin wrote this paper in which the space already appeared. So Rubin's purpose for that paper was to produce a tuple of commuting subnormal operators that does not have a joint normal extension. So as far as I know, this 1977 paper appears to be the earliest paper where the space that we call H2n appeared. So the space was also introduced by Drury in 1978 and by Arveson in 1998. So their purpose was to generalize the generalized Farnomas inequality to the multivariable setting. So Arveson's 1998 paper, it was the paper that really generated a lot of attention. I think for several reasons, we'll see. So after that, so basically, you have there are just a lot of papers. People start to study the space, and a lot of papers on the subject. So one of Arveson's main contributions in his 1998 paper is the introduction of the idea of multipliers. So a function f is said to be a multiplier if it multiplies every g that's in the Drury-Arveson space back into the Drury-Arveson space. Okay, so for this talk, we will use this notation, this script m for the collection of multipliers. Now, it's a simple consequence of the closed graph theorem that if you have a multiplier, then the multiplication operator is bounded on the Drury-Arveson space. So we will also just write so this norm with script m, the subscript, as the operator norm of the multiplication by f on the Drury-Arveson space, and that's And that's the right-hand side of the phenomenon inequality for commuting root contractions. That's what this is. Now, so for n equals 1, then as we know, the Drury-Arveson space H12 is the original Hardy space. So of course, the norm for multiplication is just the H infinity norm of the function f. So this automatically reverts back to the original phenomenon inequality, and you have such equality here. So, the reason why you want to mention this is that because in the one variable case, when n equals 1, so the one variable Hardy space or one variable Drury-Arveson space actually has an L2 space that goes along with it. It's the L2 space of the unit circle, right? This actually is important because if you want to do analysis, so what you need to do is quite often you need to do things like integration and other things. So having an L2 space really makes a lot of things easy. But once you start to have at least two variables, then the story is different. So this so in Arveson's 1998 paper, he showed that this tuple of the multiplication by the coordinate functions on the space H2n is not jointly subnormal. So the way he showed that is that so basically he produced a polynomial in these operators that turns out not to be hypernormal. So the way you show that's not hypernormal is to show that its norm actually is greater than its spectral radius. So that particular polynomial of these operators is not hypernormal. So the tuple itself cannot be jointly subnormal. So this really says that the space, the Drury-Arveson space, is really fundamentally different from these other reproducing kernel spaces, such as Hardy space and Bergman space, because as I said, if you have L2 space, then a lot of things can be done through things like integration. So on this H2n, so some of these same things, you actually have to find a way to get around the fact that there is no L2 space that comes with it. So actually, a more precise way of phrasing this is really this result of Arveson's, namely that this tuple does not have joint normal extension. However, if you look at each individual operator, each individual multiplication operator by coordinate function, so each individual one is actually subnormal, and that fact is actually important for some of the estimates. So sometimes, in other words, you don't have a global L2 that comes with the Drury-Arveson space. But for some estimates, what you have to do is that it's almost like a local L2. It's L2 with respect to a particular multiplication operator. And that's the kind of thing you need to do for certain estimates. So, all right, so let's move on. So here, this is just a reminder of what jointly subnormal means. A tuple is jointly subnormal if it has an extension that's commuting tuple for normal operators. All right. Okay. Now, it's actually so we've seen some of this in Michael's talk earlier this morning, but it's actually worth going through this proof of polynomial inequality for commuting row contraction again. So what you see here on this slide offers slightly, I mean, it's essentially the same thing, but perhaps it's a slightly different perspective. So if you want to, prove something like this, prove that it holds. How do you do that? So Drury's observation was that you can actually. So first of all, you can actually assume that this is true for some r which is close to 1. Okay. Now, once this holds, then you simply check that you have such an identity by going through some simple combinatorial manipulation. You just verify that you have such clean identity. Now, this also appeared in Michael's talk, but in a slightly different form. But as I said, essentially it's the same thing. It's really just a matter of different perspective. So I kind of like this identity. It looks kind of clean. Just this thing equals 1. The 1 being the identity operator. And so once you have this this identity, then you can simply write down this operator C, which goes from this H to n tensor H. It's given by this explicit formula, and you verify that that's an isometry. It just follows from this the combinatorial identity, and then it's just a matter of checking that something like this holds. So because this is Z is an isometry, so this implies the phenomenon inequality for row contraction. Now, there's one thing I want to mention. I guess that's something that Michael did not mention in his talk. That is, if you read Drury's paper, you have to be careful, because his tuple is exactly the adjoints of the tuple of this A1 through AN in this talk. So in other words, in other words, what's on this this slide is really a translated version of what's in Drury's paper. So A is A star is A. So all right, okay. Now, so again, it's something that you heard in Michael's talk. Now, it will be beneficial to just view the Drury-Arveson space as just one member in a family of reproducing kernel Hilbert spaces of analytic functions. For the reason that from the perspective of reproducing kernel, you will see that this comes very naturally. So so you've seen these spaces in Michael's talk yesterday, but the parametrization is a little different. So I kind of prefer this version of the parametrization. So basically, you look at this kernel, this KTZ. So you have 1 minus what you want. So 1 over 1 minus the inner product raised to the power n plus 1 plus t. The reason you want to emphasize n plus 1 is that I kind of think of n plus 1 as the starting point, because that's the kernel for the Bergman space, for the n way to the Bergman space. So you define this kernel, and the corresponding reproducing kernel Hilbert space is called HT. So you can also describe this space in a different way by explicitly describing what the inner product is between monomials. It's given by this formula. Okay. So if you go with this way for parametrization, then Well, we have this matchup between these H spaces and some of the familiar spaces. So by this scaling, H0, as I said, would be the Bergman space. I mean, I tend to think of Bergman space as a kind of really, in a way, you know, it's kind of easy to handle. Now, so that, you know, that's like the 0 point on the scale. And so H minus 1 is the Hardy space, and H minus n is the Drury-Arveson space. So basically, you know, in this approach, you know, the more negative this parameter t, the harder it is to do analysis on the corresponding space. Now, it's obvious that we actually have this kind of inclusion relation. So as it turns out, once the scale gets below -1, or once this t gets below -1, then you know, you also get this phenomenon that this tuple of multiplication operators by the coordinate functions on that space ht is not jointly subnormal. So this was recognized in 2003 by Rising and Nishian. So what that means is that if t is less than -1, H upper t is more like the Drury-Arveson space. So in other words, you run into some of the same difficulties do analysis on HT as you do on H minus n, which is the Drury-Arveson space. But still, the scale matters. In other words, even though you run into some of the same difficulties, but you know, t being equal to -n, that's, you know, sometimes it just stops certain things from going forward, basically. So here, this is something that I already mentioned. So the practical difficulty is that for these spaces, there's no L2 space. So you know, again, the trick is sometimes you don't have the global L2 space, but sometimes you have to look for a local L2 space. Okay. So as I said, you know, it's hard to get results on these spaces, but you know, there's you know, so what I'm going to do is I'm going to talk about a few things that we actually do know at this point. So one of these interesting things is the, you know, in fact, it's a relation between H infinity and the Drury-Arveson space. So in Arveson's 1998 paper, he basically looked at that function like this. So his idea is that you just multiply the independent variables together, zeta 1 through zeta n, and it's quite easy to. So it's straightforward to figure out what the H infinity norm of this function is. It's given by this, and its Drury-Arveson space norm is this, and then you just do the asymptotic. You use the asymptotic formula that turns out to be this. So you can see that this thing is a factor of k to the power of n minus 1 over 4 bigger than this. And you also notice that if n equals 1, then that factor goes away to be equal to 1. So this tells you that, you know, whenever n is greater than or equal to 2, then you just use this, you know, this difference in norm. It's quite easy to construct functions that are in H infinity, but not in the Drury-Arveson space. And you can even make this function norm on the closure of the unit ball. So it's interesting that, in fact, you know, it's already known before Arveson's 1998 paper that there are H infinity functions that are not in this Drury-Arveson space. So in Ruding's book, Function Theory in the Units of Cn, so in the last chapter, so he mentioned this result that if you have a, if there's a non-constant inner function of the ball, well then the absolute value of the gradient of the u is not square integrable with respect to the volume measure. So what that tells you is that, in fact, in this space h minus 2, already there are no non-constant inner functions. So if n is at least 2, then the Drury-Arveson space doesn't contain an inner function. Well, but the thing is that, when Rudin's book was published, in 1980, it was not yet known that there were non-constant inner functions. So this was actually constructed later, 2 years later, by Alexandrov and Low. I think they actually constructed non-constant inner functions within, I think, weeks of each other or something. So I learned this just a couple of weeks from Michael that, in fact, later in 2012, Stahl showed that the space H minus 3/2 contains no non-constant inner functions. So now, if you look at the Hardy space, which is H minus 1, that contains all the inner functions. But the space H minus 3/2 contains none of the non-constant inner functions. So the question is, if you look at this parameter t somewhere between minus 3/2 and minus 1, does the space contain any non-constant inner functions? That's actually a very interesting question, but that appears to be a very challenging problem too. So I just want to mention this. Now, so the corona theorem is actually one of the success stories of Drury-Arveson space. So in 2011, Kostya, Sawyer, and Wick proved the corona theorem for the multiply algebra of the Drury-Arveson space. So it's this statement here. I'm sure most people are familiar with what the corona theorem is. So this actually, if you search the literature, I mean, in multivariable case, there are various attempts on the corona theorem, but so far, I think this theorem is the one that that's the only one that actually deserves the name corona theorem in the multivariable setting. So in all other settings, basically you get weak solutions, solutions like in HP and other. So I think the best scenario, you can probably get something like solutions in BMO or something. But in this theorem, you start with the corona data in the multiply algebra M. You end up with a solution in the same algebra. So I think in this case, it really is a corona theorem. So so you heard this again earlier in Michael's talk. So there's the question of the causal measure for the Drury-Arveson space. So first of all, this is the definition for causal measure for Drury-Arveson space. I mean, when Causal introduced his measure, I think it was 1962, it was defined in terms of the behavior of the measure on sets. But nowadays, usually the term causal measure actually means, so it depends on your starting point. But nowadays, I think more common, the starting point is actually inequality, like this. That's a definition of a causal measure. This is a causal measure for Drury-Arveson space. So in 2008, we have this characterization by Causal, Rutberg, and Sawyer for the causal measure, for causal measures for the Drury-Arveson space. But this characterization, it's really hard to describe. So we'll just leave it at that. Okay, so there's also the question of essential norm. So first of all, if you have an operator A on Hilbert space H, so the essential norm of the operator is defined by this. Now, so for polynomials, so we know that the H infinity norm for polynomial does not dominate the multiply norm of the polynomial on Drury-Arveson space, and this is known in Arveson's paper, 1998. This was also known in Drury's paper. However, in his 1998 paper, Arveson actually showed that even though H infinity norm does not dominate the multiply norm, H infinity norm for polynomial actually equals the essential norm of the multiplication operator by the polynomial on the Drury-Arveson space. This really has to do with the fact that you heard this already, that these multiplication operators, they commute with their adjoints, modulo compact operators. In other words, these multiplication operators are essentially normal. And that's why you, and you also saw this exact sequence in Michael's talk. So you have this inequality, basically, this inequality is a consequence of that exact sequence. So Charney and I in 2011, so we figured out that even though you have such an inequality for polynomials, but for general multipliers, you don't have such an inequality. So for general multipliers, the H infinity normal still does not dominate the essential norm of this multiplication operator on the Drury-Arveson space. I think the reason actually is very simple, because for general multipliers, you don't have this essential commutativity. So there's no reason why something like that should hold. So now let's get to essential commutativity. So in his 1998 paper, Arveson already knew that if you look at the commutators of a multiplication operator with adjoints, where ij may or may not be the same. So these are compact. In fact, he showed that these are in Chatham P class for p greater than n. So this is this is something that's similar to what happens on the other reproducing kernel Hilbert spaces on both Hardy space and Bergman space. You have the same kind of essential normality for these multiplication operators. So in 2011, Charney and I, so we actually came up with this result. That is, if you look at so instead of a commutator of the adjoint of multiplication by a coordinate function was a multiplication by another coordinate function. So we will look at this kind of commutator, whereas one of them is just a multiplication by a multiplier. Well, as it turns out, if you look at this commutator, then you can actually, and this is in Chatham P class for p greater than 2n. So, roughly speaking, this kind of commutator is like half. I mean, it's, because your f is arbitrary, so you can only get half of the Shelton class membership. I mean, p greater than 2n actually in terms of so. And well, not only that, you can actually show that for p greater than 2n, it's the Shelton p norm of this is dominated by some constant which depends on p multiplied by the multiplier norm of f. Now, so the same result if you think about what happens on the Hardy space and Bergman space. Well, on Hardy space and Bergman space, this wouldn't be such a big deal because you can just write down these commutators, in terms of formulas, and you can prove this just by some very simple estimates of the kernel and so on. But Drury-Arveson space, this is not so easy. So one of the things that you need to do to prove a result like this is, you have to do what I already mentioned. That is, even though there's no global L2 space associated with the Drury-Arveson space, but with respect to each of these things, so the adjoint of each of these is actually subnormal the Drury-Arveson space. So you actually have to kind of use the local L2 space to do these estimates. The actual way of doing this estimate, it's actually quite complicated. So, all right, so this is just a reminder for definition of Shelton P class. All right, so I already mentioned this. Okay, so now let's get to the essential normality of submodules. And I only mentioned submodules here. I should include quotient module as well. But so again, that's something that you already heard plenty of, particularly from yesterday Yuan's talk. You heard plenty of it. So in any case, so suppose you have a submodule of the space HT. So it's so it's essentially normal if you look at this restricted, like you restrict the multiplication operator by coordinates onto the submodule. So you get these restricted operator, and you look at these commutators, and of course, the star here, the adjoint is taken on the submodule, right? So so this is said to be essentially normal if the commutators are compact. And so that's said. So this is said to be, the sigma is said to be p essentially normal if all these commutators belong to the Shelton class CP. So in about the year 2000, Arveson proposed this conjecture, which says that every graded submodule of H2n tensor Cm is essentially normal. So graded simply means that you actually have an internal orthogonal decomposition for the submodule in terms of degree of polynomials. But the problem becomes, so for graded modules, essentially it's, to prove essential normality, it's most of the work actually is algebraic. But the problem becomes more analytical if there's no orthogonal decomposition in terms of polynomials within the module itself. So later in 2006, Douglas proposed a similar but refined conjecture for the Bergman space. So the refinement really lies, I guess, on my slides. I didn't mention the quotient module. So the refinement really comes when you look at the quotient module. So for the quotient module, you actually have improved the essential normality. That's a refinement. So as far as Arveson's original conjecture goes, I think the best results are due to Guo and Wang going back to 2008. So in the case n equals 2 and 3, then they prove that every graded submodule of H2n is p essentially normal for p greater than n. For n that's arbitrary, then every submodule generated by a single homogeneous polynomial is p essentially normal for p greater than n. Now, in 2011, so Douglas and Kai Wang published this result. This actually came as something of a surprise because, as I said previously, most of the works were about graded submodules, where the work is basically algebraic in nature. So in this 2011 result, they showed that for every polynomial Q, the submodule of the Bergen module generated by polynomial Q is p essentially normal for p greater than n. So in other words, there's no restriction on what this Q might be. So this actually kind of changed the game, because once you start dealing with these arbitrary polynomials, then the method for proving essential normality just turns completely into something that's different. So this is, it's nice that it's an unconditional result in that it makes no assumption about the polynomial Q. So Trina and I, figured out in 2013 so all these dates are really publication dates of the paper. So we figured out that if you look at all the weights that are above -2, then for any polynomial Q, the submodule of HT generated by Q is p essentially normal for p greater than n. So this in particular includes the case where t equals -1. T equals -1 gives you the Hardy space. So basically that's this is the analog of the Douglas-Wang result for the Hardy space. And that was actually one of the things they specifically mentioned in that paper, that that they say that should be true, but they didn't see how to do it. So in 2013, we generalized their result to cover this range of weights. Well, later in 2018, we actually improved our results so that this range of weights are now covered. So if t is anywhere between -3, being strictly greater than -3, but less than or equal to -2, then any submodule generated by any single polynomial of HT is p essentially normal. So what's nice about this is that it includes the case where t equals -2. So t equals -2 just gives us just this one single Drury-Arveson space. So a particular corollary is that for this Drury-Arveson space, the case n equals 2. If you have any two variable polynomial, then the submodule generated by it is actually p essentially normal for p greater than 2. Now, so here, if you look at our results, so we were basically like on the doorstep of -3, right? So if you can somehow get to -3, then you will get at least another Drury-Arveson space. But there just in other words, even this marginal improvement, it's like you hit a mountain or something. You just couldn't do it because there's a technique that basically ends at this point. So as I said, in this business, the value of the weight really matters. Sometimes, you can just be on the doorstep, but you just, it's really hard to get into the door. So anyways, let's see. Okay, so let me just briefly mention the problem characterization of multipliers. So the big mystery about Drury-Arveson space is really membership in M, the collection of multipliers. So unfortunately, so far, there's really no good characterization of this membership. Even if you go back to Arveson's original paper, so you think about what we know from there. So we know that from Arveson's paper, we know that the finiteness of this H infinity norm does not guarantee this membership, right? More generally, if you have a H which is in the intersection of the Drury-Arveson space and H infinity, then this thing does not dominate the H infinity norm of H. Now, if you ask, a more refined question, say, suppose I have an F which is in the intersection of the two. Does that mean that F is in the multiply algebra? Even that kind of answer, was not known at the time. Again, you heard this earlier. So in year 2000, Fabrega, Ortega and Fabrega produced this result. So they showed that if you have an F, which is an element of the Drury-Arveson space, well then, let's see, right. So they look at this measure. So their result is that F is a multiplier if and only if this measure is the causal measure for the Drury-Arveson space. Now, if you combine that with this 2008 result, where you have a characterization for the causal measures for the Drury-Arveson space, the combination of the two is a characterization of membership in the multiply algebra. But unfortunately, this characterization of causal measure in general, that just looks too complicated. So, I mean, it's a characterization, but it's not really a satisfactory characterization, I would say. So the question is, is there a simple way of, or more direct way of characterizing this membership? Now, because Drury-Arveson space is a reproducing kernel Hilbert space, so you would naturally think about the normalized reproducing kernel. So you look at the normalized reproducing kernel. I mean, you might actually look at like the Berezin transform of an element F that's given by this, but that's just equal to F of Z. So that's only not enough, right? That we know. But what about something that's stronger than Berezin transform? So Charlie Fine and we actually thought about this problem for several years, basically. So suppose, I mean, it's kind of a natural problem. So if you take an element F in the H2 space, you look at this condition, say if this is a finite, so does that imply that F is a multiplier? So initially we thought that there's at least some chance that this, the answer might be affirmative. But it turns out that that's not the case. In fact, it's just the opposite. So, what happened, it turns out that, you can find elements in the H2s in the Drury-Arveson space, which is not a multiplier, but nevertheless, this holds. So this at least says that, you know, in general, you know, this membership does not imply this membership. Let's see. I see that my time is up, even though I still have 10 slides, but I think this might actually be a good place to stop. So I'll just stop my talk here. Thank you.
Thank you very much.
Thank you.
Let's thank Jingbo for wonderful talk.
Thank you.
Questions, comments, suggestions? If not, let's thank Jingbo again.